seminar. Now we have two talks today, and before that, I would like to make an announcement that Professor George Kanedakis will not attend today's online seminar due to health issues, and I apologize to the speakers today on his behalf. He will watch our recording later. Okay, our first speaker is Professor Zhiwen Zhang from the University of Hong Kong. Professor Zhang joined the university as an assistant professor in 2015 and became associate professor in 2021. Before joining the University of Hong Kong, he was a postdoctoral scholar at Caltech from 2011 to 2015. Before that, he obtained his bachelor and PhD degrees in mathematics from Tsinghua University. Professor Zhang's research mainly focuses on scientific computing. His interests include uncertainty quantification, numerical methods for stochastic differential equations, numerical methods for partial differential equations arising from quantum chemistry, wave propagation, multi-scale porous media, nonlinear filtering, data simulation, and stochastic fluid dynamics. So welcome, Professor Zhang, and you may want to start the presentation.
Thank you, Zhongren. Can you hear me? Thank you.
Yes.
Okay, so first of all, I want to thank Professor Kanedakis very much for your kind invitation, and I hope you will recover soon. And also thank Zhongren and Samadotas for the scheduling this time for me. Okay, so today my talk is I want to introduce this so-called DeepParticle method to you guys. So this title is very long. You can see here. I will explain why I have this long title. And this joint work with my former student, Dr. Wang Zhongjie. And he's currently at the University of Chicago as a postdoc. Then he will join the Nanyang Technology University in August. And also with Professor Jack Xin from UC Irvine. Okay, so let me, the outline of today's talk is the following. So first, maybe 20 minutes, I briefly introduce this previous work, so-called the interacting particle method, because I want to explain, because we developed this so-called DeepParticle method from this previous work. So I will explain some basic idea and some results, and give you motivation. Why do we need to develop this DeepParticle method to reduce the cost? So this is the first part. Okay, then so I know this audience many focus on machine learning related research. So this part is not machine learning at all. So this kind of like a physics and background and numerical mathematics. And the second part is I want to briefly introduce the so-called DeepParticle method for learning invariant measure, such as how to design the penalty function and some iterative method. And the third part is some application of this DeepParticle method, such as using this method to compute KPP from speed, invariant measures, and also to learn and generating some aggregation patterns in kilo-signal system, and also some byproduct result and conclusion. So I hope this combination will, that's my plan. So let me quickly move to the first part. So this first maybe 15 minutes or 20 minutes is not machine learning at all, but I give you some motivation. So I will do quickly. So I studied this problem, so-called front propagation in complex fluid flows. So this has many applications in many areas, such as turbulence combustion, chemical kinetics. So basically, this fundamental question is want to study, analyze, and compute the large scale front speed in complex flow. So for example, a model problem is this reaction, diffusion, advection equation, this one, with the KBP nonlinear type. Okay, so here this operator has three parts: the diffusion part, advection part, and the reaction part. This is a very interesting problem. And when this FU equal U minus times Y minus U, we call this KBP nonlinear type. And there are several parameters. Kappa is a diffusion parameter. Tau is this time scale parameter for the reaction rate. In this work, we we fix tau equal 1. So we choose this scale. And there are also parameters from V. That is the magnitude of this advection. So you can see if kappa is very small or the magnitude is very large, then this problem is difficult to solve. So this research has been studied for decades since the pioneer work of Kolmogorov and other mathematicians. So many mathematical analysis and numerical works has done for the flow of fluid is well structured, such as regular motion, cellular flow, or some fully random motion. However, some often encountered but less studied was the case that this streamline contains both a regular and irregular motion, such as some chaotic flow, such as ABC flow, K flow, the typical chaotic flow. So how to study this front speed? So the nonlinear problem difficult, so people linearize it. So when the velocity field is time independent or steady flow, so in this case, the minimal front speed in direction E is given by this variational form here, C star E equals this. So here this mu lambda. Mu lambda is a principal eigenvalue of this elliptic operator, this operator. And so that means we need to compute the eigenvalue, principal eigenvalue of this operator by any numerical method, such as finite element or spectral method. Then you compute this ratio and pick the inf, and you can get this minimal propagation speed. So this has important physical application importance. All right. So this is a time independent case. So when the flow is unsteady or time dependent, this variational formula still exists. So in this case, we need to solve this principal eigenvalue for this parabolic type, time periodic parabolic operator. You have this additional term here. So this time dependent makes the problem even harder. Means you have an additional degree of freedom. So in the literature, there's some work using some edge average FEM with algebraic multi-grid method to compute this only for 2D. So here, when problems are defined in 3D space, and when the problem are advection dominant, diffusion small, very small, or this advection is strong, so this will bring challenge for numerical method such as FEM or spectral method. So that is the situation. So we have some previous work. We developed some particle method to compute effective diffusivity in chaotic and stochastic flow. So this motivates us to develop a particle method for computing KBB front speed. Okay, so that's the motivation. How to do that? It's we need this so-called Fokker Feynman-Cass formula. Okay, so look at here. We consider this linearized equation here. Then actually this principal eigenvalue is given by this formula. So this principal eigenvalue is actually the Lyapunov exponent of this parabolic operator. Okay, then if you, as I mentioned again before, if you solve this problem 4 by FEM, when kappa is small or when D is 3, this is becoming expensive. So we need to design other methods. So here, so how to develop a particle method? We use this Feynman-Cass formula. So we split the operator A into L plus C. L is the diffusion and advection part, and C is the potential part. So from the operator L, we can construct an SD system as the following. This drift term just from this advection here, velocity here. Then this diffusion part comes from here. Okay, this is pretty easy. All right. So then the Feynman-Cass formula is here. So that means I give you that the principal eigenvalue have this beautiful formula, equation 7. this is very beautiful mathematically, because the Feynman-Katz formula builds a connection between SDE and the parabolic type PDE. That's very elegant and nice. However, okay, sorry, this expectation is over all the randomness induced by a Brownian motion. All right, this is a beautiful formula. However, if you directly get samples from 6 to get this and plug in and compute this, it's numerically is unstable. Why? Because this term, look at this term. You need to compute the exponential function. So we know this exponential function is highly non-trivial. Some number can be, large number. If you take exponential, it can become very large. So this cause some instability. Okay, so how to cure this instability? If you remember in the power method, for computing the eigenvalue of matrix, and we use the power method a lot. We just multiply vector and normalize it. Okay, so similar to this idea, we can study the Feynman-Katz semigroup. All right, so the Feynman-Katz semigroup so we can actually you can find that compute the principal eigenvalue is equivalent or related to study the convergence of the Feynman-Katz group associated with the SDE system potential. Okay, so let me introduce some notation. TD is the set of probability measure over TD, and S is the smooth test function, and we can define the evolution operator P here. Okay, so and also define the counterpart, is a weighted counterpart here. The C, small c, is potential. Okay, so one can easily verify equation 8 and equation 9. The generator of this operator and this operator are L and capital A, respectively. So, all right. So, equipped with this definition, we can define the Feynman-Katz operator. This is essentially you can compare. You can view this as a power method. Okay. So you evolve the density. One step and normalize it. All right. So one can easily verify this Feynman-Katz operator satisfy the semi-group property, and for our example, if your velocity has a period t in time, we choose this period as a capital T. If the velocity is steady, does not depend on t, we introduce artificial time, and for example, you choose t equal 1. Okay, that's a setup. Then we can introduce n. N is the iteration time. So for example, if you iterate n times, you get this operator nt equal 1t to the power n. It's a composition operator. So a very elegant and beautiful property for this Feynman-Katz group is this. So if the operator A has a spectral gap, the first principal eigenvalue and the remaining spectral, there is a distance, positive distance, then for any measure nu, and if you evolve this Feynman-Katz semigroup, it will converge to the inverter measure exponentially fast. Okay, so this is a very beautiful result. So this is a foundation for our method. All right. So that means we choose any initial measure. We evolve this Feynman-Katz group, semigroup. Then when the measure converges to the inverter measure nu c, and we can do some integration. Then we can this quantity approximate the principal eigenvalue or converge to the principal eigenvalue. So this is this provides us the algorithm to compute the principal eigenvalue. Okay, so let me quickly go over the several slides. This it's how to numerically discretize it. For every delta t, capital T is a period. Capital T is a period. We further partition into m part, and delta t is the time step. So we evolved the SD by this Euler-Maruyama scheme. So this defines the evolution operator. Then this approximate this part in this accuracy delta t square, and then we can approximate this semi-group Feynman-Katz semi-group by some integration rule, such as a right point rectangular rule, and this Feynman-Katz group time discretization. Time discretization have this can be written as equation 17. One more thing means here so far we don't discretize the measure here. In practice, we don't know. This part is more difficult. We cannot evolve measure because this is complicated. We have to approximate this measure by empirical distribution. So we choose capital N sample point according to initial measure, and we use this empirical distribution to approximate the any measure. Okay, so we call this uninteracting particle system. All right. So for example, give any, so pi 0 is the initial measure, and this evolution define a Markov process defined in a product space TDN. That's the initial distribution, and from n-1 to n, we evolve this distribution, empirical distribution, according to this Feynman-Katz semi-group. This from n-1 to n until do this iteration until this empirical distribution converge to the invert measure. Then we stop. Then we use that invert measure kind of integration or summation to approximate the principal eigenvalue. That is the basic idea of this interacting particle method. All right. So
excuse me.
Yeah.
Can I ask a question? This is Panos Tinis from Pacific Northwest National Lab. So because you call this capital N interacting particle system, where does the interaction come from?
Oh, that's a nice question. Thanks. The interacting means that means we need to do the resampling.
Okay, so it's like a particle method, right?
Okay. That's a very nice question.
Okay, so it's not so you can evolve each particle individually, but when you do the resampling, that's you get the weights, right? Okay.
Exactly.
Okay.
That's a very nice question. I know this interacting particle method is a very large community solving SD. Like I will show you later. That's another kind of like a McKen-Vlasov equation. You also have this interacting system.
And just a follow-up question, since you mentioned now particle method, that for particle methods, usually there is some kind of observation that you use to define a likelihood function, so that in equation 22, you can define the exponent. Here, you use the potential from what I see, right?
Yes, exactly. Yes.
Okay.
All right. Nice. So thanks.
All right.
Yeah.
Okay. Thank you.
Thanks for the nice question. Yeah. Thanks for a nice question. Very nice. So this slides show you the iteration from n-1 to n. We do this Feynman-Katz we evolve the Feynman-Katz semi-group, and as the audience asks, why do we call this interacting? Because within each period, we need to partition this capital T into m parts, and we solve this SD one step, and do the resampling one step again like this. So here is the diagram. So within one period from n-1 to n, we solve this SD delta T step and do the resampling one step, and again until M step, capital M step, capital M step, and we get the initial data for next period, for next iteration. Okay, so this is the algorithm. So I'll quickly finish this because I want to teach you more about deep learning part. So if you want to know more about this algorithm, you can check the paper, okay? So in this computation, every step, we get this change of mass. And finally, sum together, and we get this quantity 25. That is approximation of the principal eigenvalue, mu and delta t lambda. So here, in this formula, we have 3 sources of error. Number 1, from Monte Carlo capital N, from Monte Carlo error capital N. Second is delta t, and the third is the iteration small n, small n. So this, theoretically speaking, you can say I choose a capital N large enough such that this sampling error is negligible. Then we mainly focus on the error come from delta t and small n, these 2 sources of error. So I quickly, so this error analysis part is boring, technical involved. I quickly skip. If you want to know more, you can check the paper. And the final result is this. So this is a numerical approximation, and n approach infinity. If you n does not approach infinity, there's an additional error square root of 1 over square root of capital N, the Monte Carlo error. The 2-term error, this part is from the iteration, and this error is from the time step, the delta t iteration. So basically, this equation 35 provide a very rough error estimate for this interacting particle method. This parameter E epsilon and gamma come from the this Markov process iteration error. All right. Okay. Then that's the analysis part. Let me show you some results that give you the motivation. Why do we need to develop the particle method? So first, several slides is a convergence result. For 2D cellular flow, 3D ABC flow, we solve this. Okay, these 2 are time independent. 2D cellular flow, 3D ABC flow like this. We solve this elliptic type eigenvalue problem. The reference solution is obtained by spectral method. So here is some convergence result. It's about much better than the error analysis because error analysis is very rough. Then here we also investigate this unsteady flow, time dependent flow. So in this case, the flow velocity depends on time. So we need to solve this parabolic type PDE eigenvalue to get a reference solution. However, imagine, guys, if you solve SD from 2D to 3D, from time independent velocity to time dependent velocity, the computational cost is similar. That is one of the advantage of a particle method. Okay, so yeah, here is some this result for the time dependent flow. Then okay, so for this some pure PD guys or physicists, they are interested in some power law, such as, for example, how does this C star depends on A? A is the magnitude of your velocity. How do you have some power law for this relationship? We do to do this, we do some scaling analysis. Well, in the literature, for the 2D cellular flow case, people can rigorously prove they have this relation. C star A equal A to the power 1 over 4. That's the analysis result. Also, for the effective diffusivity of this type flow, they have this relationship. That's the effective diffusivity. So that means you have equation 40 means C star and effective diffusivity have this square root relationship. So this is very nice because this provides some guidance or verify our result. So for the 2D case, because in my previous work, I already compute the effective diffusivity for this type of flow. So I can, in this work, I compute the front speed. So I get the two results. So I can verify whether this relationship is true. So this relationship, so let me say this in this way. This already proved by TD guys. So this provide a guidance to verify my algorithm. So this is true. And for the 3D case, I also compute the front speed and also compute the effective diffusivity. So here, when sigma is very small, we can numerically verify. Okay, just numerically show that this relationship is also true for K flow. However, we don't know how to prove it at this moment. This can be a future work. All right, let me move to the particle case, DeepParticle case. So let me show you. So in the particle method, if you involve these particles, you can get this empirical distribution. So if this empirical distribution converts to the invariant measure, you can plot out. You can see when sigma is small, when sigma is very small, it's like this advection dominant case. So this distribution become very concentrated on some point. Okay, so in a time periodic case also has this pattern. And here, let me show you this picture. When sigma is very small, when sigma become very small, you can see the invariant measure develop some sharp gradient, develop sharp gradient. So here's the question. If you want to compute the KPP front speed for different sigma, so if your initial guess is a uniform distribution, okay, uniform distribution, when sigma is large, you may need like 1,000 iteration or maybe 500 to get this. However, you may need 10,000 or more to get this one, sharp gradient case, right? So that means when sigma becomes very, very small, you need more iteration. You need more iteration to compute the KPP front speed. Okay. So here's the question: Can you develop some good idea? Can you develop some good algorithm? Can provide some good preconditioner or good initial guess, good initial data for the iteration for small sigma, right? If you can, then you can use this guy as a preconditioner and you can quickly convert. All right. So that's the motivation. Why do we study this DeepParticle method? Okay. So we want to reduce this particle cost. That's the beginning of DeepParticle method. Okay. So so far that's the physics part, because I'm a numerical scientific computing guy. I'm not an expert in machine learning. So first, I do research in this scientific computing. There is some need. I need a faster method. So this motivates us to develop using this deep neural network to reduce its cost. Okay. So this motivates us to develop DeepParticle method to learn the invariant measure by neural network. So how to do this? We minimize the Wasserstein distance on the data generated from interacting particle method. So this is very long. However, I hope I explain the basic goal of this research. All right, then let me move to the DeepParticle part. So this part will be much easier to understand. So to train the network, we need a loss function. So here we study these distributions. So a very natural idea is Wasserstein distance. So definitely we can study like a KL divergence or Hellinger distance or other type of distance for distribution. But in the first step, we consider Wasserstein distance. So for example, you have two measures. You can define the push forward map, such as map this measure to another one. And we can compute this discrepancy by computing the Wasserstein distance between two measures. Here, gamma mu nu is a joint distribution on this product space, such as if you integrate one variable, you get a marginal distribution for another. So in this case, we studied this particle distance in Euclidean space, so we choose p equal 2. All right, this part is a very rigorous. However, in practice, we sometimes we don't have a closed form for the distribution, and sometimes this computational for analytical formula can be difficult. So we use this empirical distribution. So for mu and nu, we use this delta summation or delta function as empirical distribution. Okay, and in this case, this joint distribution is represented by this n by n doubly stochastic matrix. They satisfy all the elements are non-negative, and this additional constraint, such as this marginal distribution is a probability. Okay, so you can say this empirical distribution function has some freedom that allows us to approximate different measures. All right, so in this discretized setup, we can discretize the Wasserstein distance in this way. All right, so here, so we want to do this. We want to train a deep neural network f theta x eta. So here x is the physical input. So in my example, that is the particle position. Eta is some parameter, physical parameter. They also input. In my case, you can view this epsilon, the diffusivity parameter, or parklet number as a physical parameter. That's also input. And theta is all the trainable parameter in the neural network. Okay, this will be updated by the SGD, Adams SGD. Okay. Then we have so that's a one pair distribution, and actually, you know, from this different set of training data, you can choose several pair, like from here to here, from here to here, from here to here. You can get several pairs of training data. So you do a summation for all these different pairs. Okay, then you get this training loss function like this. So this is very simple. That's our first choice. Definitely, you can define better loss function. That can be a future research idea or work. So, all right. Then as I said again, we update the theta by SGD Adams, and we also update this gamma by LP, that's a linear programming method. Okay, this is very easy to understand. However, the difficult part is when the particle number is large, the degree of freedom, the complexity of this optimization is very expensive. For example, when n is 2000, that's not large that's not a large number for particles. However, the degree of freedom always is already n squared, 4 million. So it's urgently need to develop some fast algorithm. Some efficient algorithm to reduce the cost. Because I'm a scientific computing guy. I know some like a domain decomposition, like a Jacobi iteration, Gauss iteration, this kind of idea, like a domain decomposition. So this motivates us to develop a so-called mini batch linear programming algorithm. The idea is very simple. Instead of solve a large optimization problem with a degree n, I choose a sub problem, like a domain decomposition. I choose a subdomain M. This M is far less than n. I randomly choose M row and M column. I have this sub problem. This is my loss function. So satisfy this constraint. So I mean, you have a large matrix. You randomly, every time you randomly choose a sub block, you minimize this part, right? So this is like a domain decomposition, and so this will reduce the cost. This will reduce the cost. Okay, so because the optimization for gamma and the network are minimizing and minimizing, so we solve them alternatively. All right. One more beautiful thing here is this. When the training is finished, this network can be viewed as a sampler. So that means you, for example, you use 1,000. You use 1,000. Your training data set is 1,000. But after training, you can input 10,000 or 100,000 input, and you can get a corresponding output. So in this case, you can view this as a sampler. Okay. So, well, here is our network. I know here audience are expert in like a designed architecture for neural network. So I'm sure you can design much better network than me. Okay, so yeah, that's just a very simple network we used in the paper. So X is the physical input, eta is the physical parameter input. That's layers. All right, so let me show you some example. First one is the training is we want to learn the map from uniform distribution to Gaussian distribution with a parameter e. This different variance. Second, so this is very nice. This is a very nice, interesting result. So return to my KDD front speed project. So okay, to be honest, we don't have large computational resource. So we use a desktop or laptop to do. So here, this parameter is actually not very small, but just to demonstrate some idea. You can see when sigma becomes small, the density becomes sharper, just a little bit. And you can see this second row is obtained by IPM, and the first row is obtained by the deep network. Qualitatively agree with each other. And one more beautiful thing is here. After you learning this network, you input an even smaller sigma, and you get this predicted inverter measure by neural network. The left part is ground truth, and the right part is obtained by our method. See, they are not exactly equal. However, you know, if you use imagine you use initial uniform distribution to you maybe need 10,000 iteration to get this ground truth inverter measure. However, if you use a network as a preconditioner, you know, you use this guy as an initial distribution, you may need like 1,000 or maybe 500 iteration by IPM, you will get a convergent inverter measure. So in this sense, this DeepParticle method can be viewed as a preconditioner for IPM. I want to demonstrate this idea.
Yeah,
okay.
Professor Zhang, can I ask a question?
Yeah, go ahead, please.
Yeah, for this figure, the result, the sigma, this level sigma, is it included in the training range?
No,
or is
a little bit extrapolation, a little bit.
Yeah, so it is a result of extrapolation. Okay, yeah, that's very good, I think. Yeah,
a little bit tiny. Let me show you some later.
Yeah, thank you.
Okay, thanks for the nice question. As I said again, we have limited resource, so this number is actually not small. Okay, so let me move to the next application is learning and generating aggregation patterns in the Keller-Segal chemotaxis system. So we are not an expert in PDE. This is a very famous model in the mathematical modeling part. So this KS equation model this organism directly their movement towards the gradient of some chemical concentration, such as bacteria. You know, 2D you have this 2D or 3D you have this parabolic equation. Rho is the density of bacteria. C is the density for the chemical concentration. So, this is some biology thing, but because this rho is some density, so we can use this provide a model to investigate our DeepParticle method. Okay, so when the chemical reaction is much faster than organism, and we can choose epsilon approach 0. So this parabolic PDE become elliptic PDE, make the story easier, and you can solve this elliptic Poisson equation and plug in here. You get this one. One more thing, in practice, you can also add extra, like external advection velocity here to test what is if you add some extra or external velocity flow, what happened for the biology system. So here in 2D elliptic case, so this equation is solvable. You have this green function, plug in, you get this McCain-Vlasov equation. Then you can solve this by this particle system. So here is the true interacting particle, because for each position, you need to consider this interacting. Okay, so here, if you directly solve this McCain-Vlasov equation by this SDE, it's not easy. Some difficulty come from number one. Every step is expensive. Every step there's n particle. Each term there n summation, so it's O(n) squared. It's very expensive. Well, you can design some fast multiple type method to reduce the cost, but that's another research direction. Another difficulty come from this kernel is singular, so that means look at for example the green function is singular. So that means when two particles are close, you have some numerical instability. All right. So how to do this? There are many other interesting directions. Here we do this. We replace this singular kernel by some smooth kernel, regularized kernel, and we want to investigate this DeepParticle to learn and generating aggregation patterns. So that means we use an expensive solver to solve this. We get some training data, and we want to see whether the DeepParticle method can learn the dependence of this distribution on the parameter. Here, the parameter can be time t. The parameter can be time t, or the magnitude of this velocity. Okay, so let me show you. First, when the advection is 0, there's no advection. If for the 2D problem, there's a well-studied subject. The people prove that when the initial mass over is bigger than the critical mass, and this system will blow up in finite time t equal this time. Okay, the solution will blow up. So we in this case we view t as a parameter. We generate data from 0 to 0.1 every 0.01 unit. So we get 11 training data, and we given this 11 training data, we apply the DeepParticle. Hope we can learn the dependence of this aggregation pattern, dependence on time t. So this is some result. So you can see when t is t equals 0.1 is the largest time in the training data, and we input t equals 0.12. That is a kind of a little bit extrapolation, because this data is not in the training data, and qualitatively you get some result. Okay, yeah. Next is we have this laminar flow. We add additional flow V, and the magnitude is a parameter A. Is a parameter. We fix time T. We fix time. So again, the training data is obtained by ranging from 0 to 100 every 10 unit. So this interpolation. Then also this one is 150 is extrapolation because this data is not in training data. So there's a theory, not a theory, but some experiment, numerical result in the literature show that by adding this external velocity field, they can postpone or there's no blow up. Okay, so you can see this. I mean, if the magnitude of velocity is very strong, this will blow away all the bacteria, so there's no blow up. And also we can also compute 3D example, 3D. So I also say one thing is this interacting particle method and the DeepParticle method, they are, you know, for 2D, 3D, the scalability is okay. Because however, if you use a finite element or spectral method from 2D to 3D, it's very, very expensive. So that's one of the advantage of this particle type method. Okay. Yeah, this is some result. And finally, I want to show you one more thing is as a byproduct of this DeepParticle method, we want to converge. We want to prove that this method is convergent. Okay, that's a byproduct or additional project, and we you know, OT is a popular research area. Then in the Kononovich's setup, OT is reduced to a linear program. So if the size of problem is small, you know, simplex method or interior point method are very powerful, right? Then if the scale, if the size of problem is large, then this problem become expensive. You know, SYNCO is a very popular method to solve this type of OT problem. But SYNCO method, you need to add some relaxation term. So when the relaxation number is large, the solution is will be affected. When the relaxation number is small, and there's some numerical instability issue, well, there are many research to stabilize the SYNCO algorithm. That's a very hot research topic. So here, I don't say this method is better than SYNCO. I don't say this. I just want to say this random block coordinated method provide alternative solver, efficient solver for the OT problem.
Excuse me, quick question.
Yeah.
In the previous slide,
yeah,
in the last bullet, you talk about an accelerated version.
Yeah.
What is this accelerated version?
Accelerated means for this we can prove some convergence. However, we need we have some trick to speed up this algorithm, random block coordinated descent method. The performance is improved. However, we cannot prove this version.
Right, but what is this trick?
We create some basis so that can tell us which kind of index to choose will achieve faster convergence.
Okay, so it's not that random anymore. You have an educated guess of how to pick
right. That's right. Here, for example, I just say randomly choose M index, right?
Right.
So this is fully random.
Okay.
So there's not like educated choose, right?
Okay.
However, if you consider some, if you add some more information, add some more smarter choice, then you can speed up.
Okay.
However, we don't know how to prove the convergence. We are still working on this. I just want to say this DeepParticle, that's a byproduct of this DeepParticle method. So this is a fascinating research area. we are still working on this. So let me see the conclusion, because I'm still almost running out of time. So yeah, our research on DeepParticle is also inspired by a physical problem, KPP problem. So we first developed this IP method to compute the principal eigenvalue of advection diffusion operator. This can compute the front speed in KPP problem. Here I want to have a remark. This method can only compute the principal eigenvalue. Okay, if you want to compute all the eigenvalue, or maybe first few eigenvalues, the only choice is a finite element or spectral method. The key ingredient of this IP method is to involve this empirical distribution or particle until this converges to the inverter measure, and then this front speed can be computed from inverter measure. So this method is mesh-free and self-adaptive. To speed up this computation for KPP front speed, motivates us to develop the DeepParticle method. Okay, then this in the first example, the parameter can be the Park-like number or Park-like number in the KPP problem. However, this method can be extended to other settings, such as to learn this to learn this distribution or inverter measures for stochastic differential system, or maybe one example is to learn this aggregation pattern in Killer-Segal chemotaxis system. So if you have other application, we can do that together. I mean, there are many. I think there are other possible research direction we can explore. So thanks very much for your attention. That's all my talk. So yeah, that's it.
Thank you, Professor Zhang.
Mm-hmm.
Yeah, I actually have a question. Could you go back to the slide where you show the structure of your neural network?
Yeah. Yeah.
Yeah, here. So so here this x is a scalar, and this so in the numerical example, this eta is actually sigma. It's also a scalar, so some parameter, right?
X can be a vector, like a particle 2D, 3D. Then there's a 2D vector or 3D vector.
And is it f of x a scalar too, or it can be a vector as well?
So far it's a scalar.
Okay, so from based on my understanding, so you're learning a mapping from a measure to a measure.
Yeah.
So between fields, basically.
Yeah.
So why don't you use something, because currently there are many techniques from computer science community, like convolutional convolutional neural network stuff. So if you're learning fields to fields, so maybe I think some convolutional techniques will help a lot on this one. So and basically you're learning a conditional mapping, and then the mapping condition is conditional on eta, on the parameter, right?
Yeah.
Okay, yeah. So okay, I just want to make sure. Thank you.
Thanks for the suggestion. I will consider that. Thanks.
Yeah, thanks. So I see. Do we have any questions? I see.
Yeah, I have a question.
Yeah, go ahead. Yeah.
Thank you for the talk. I appreciate the evolution of measures, but specifically for the Keller-Segal, there is an underlying field, which is the food field. Unless you consider the evolution of the food field, or unless the food field is known and fixed, then you cannot go from measure to measure. Okay, so if you want to learn Keller-Segal, you have to include in some way the gradients of the chemoattractants or the food or something.
You mean here?
Yeah, there is the grad C in addition to the grad rho.
Okay.
You are learning. I mean, you're assuming grad C is like known or fixed or something. Okay, it's fixable. I just wanted to make sure that you dealt with it or did not deal with it. Because most of the PDs that everybody learns are usually, not everyone, but a lot of them are translationally invariant. And so you don't have to worry about the grad C. But the grad C here makes the thing not translationally invariant.
Okay, okay.
Yeah. Thank you.
Okay. Thank you, Professor. Thank you.
Yeah. Do we have more questions for our speaker from the audience? All right. Thank you, Professor Zhang, for your wonderful talk.
Thank you. Thank you.
Yeah, just for your information, we're recording this, and after the seminar, maybe during the weekend, we're going to upload the recording to the YouTube channel. We have a YouTube channel for Crunch Seminar. You may want to search that. And yeah, we're putting, uploading every week's recordings on that channel.
Yeah, that's a very nice thing. Thank you for organizing this. That's a very nice thing. Thank you.
All right, so let's move to our second talk. Our second speaker is Cristina, who recently obtained her PhD from the Department of Mechanical Engineering at Johns Hopkins University. Her PhD work was advised by Professor Yanis Kavrakidis, and she is developing novel data-driven methodologies to efficiently model the dynamics of real-life complex systems that require expensive and detailed simulations. She received a dual degree from the University of Granada in Spain and a master's degree in mechanical engineering from Johns Hopkins University. And Cristina has been recognized by MIT as a rising star in mechanical engineering. Cristina, welcome, Cristina. You may, can you hear me?
Yes, can you see my presentation?
Yes. You may want to start your presentation,
Yeah, so thank you so much for the kind introduction. The topic of my talk today is going to be focused on one of the papers that I work on during my PhD, and it's about using physics-assisted machine learning models in a complex fluid dynamical system. But first, I just want to give you a general idea of the work that I've done during my PhD. So essentially, I've worked on developing and applying the equation-free and variable-free closure approaches using techniques such as machine learning and manifold learning to model the unresolved dynamics that are governed by either partial differential equations or stochastic differential equations as functions of low resolution observables. And these algorithms have been validated in a number of different example problems. One of them is a thin-film flow that is going to be the focus of my talk today, a multi-phase flow, an agent-based model, and the Kuramoto-Siusinski PDE. So in one paper, the PDE for the amplitude was predicted or learned as a physics-informed reduced order model in a thin film that has wave patterns. And in addition, we show that we can predict the full velocity field from partial amplitude data. And in another paper, we computed in a local approach local closures for the PDE of coarse grain and Navier-Stokes equations for a two-dimensional multi-phase flow. And we also learned the dynamics of the ODEs in a global approach for the average fields. And I've also worked on SDEs for reduced order model of the collective behavior at the tipping point in a population of interacting agents. And then the most theoretical work has to do with post-processing Galerkin in a data-driven fashion for dissipative PDEs. And so the focus of today's talk, once I give you a general idea of what my work is about, is focused on the paper of the thin-film flow. A little bit of background for the thin-film flow. So we have a flow of high surface tension liquid that is flowing down an inclined plane under the action of gravity. And this type of flow presents very interesting surface dynamics and has attracted significant attention since the first experiments that were done for this type of flow by the physicists the Kapitsa family in the mid-40s. And here I'm showing you a few pictures from those experiments back then. And this problem it has, as I mentioned, very interesting wave patterns, and there are many papers regarding looking at the nonlinear dynamics of these patterns. So there's a nonlinear analysis have been proposed to accurate and efficiently compute the height of the film for this type of flow. And the Navier-Stokes equations that we all know are accurate, however, require significant computational resources, and especially for this type of flow, where knowing the amplitude of the film instead of full velocity fields and pressure fields is more than enough to understand the dynamics. Using Navier-Stokes is not computationally something that is advisable for this type of situation. So instead, coarse-grained equations have been proposed as efficient alternative, but these, however, are only valid under some assumptions. And there is a hierarchy of models in the literature that here are presented in order of descending generality. So on top of them, we have the high resolution Navier-Stokes model, which is accurate for any Reynolds number. And then we have what are called the boundary layer equations, which are derived assuming a long wave. We also have a less general type of model, which is called the Benny equation, which is derived in addition to the previous assumptions for a small Reynolds number and a high surface tension liquid, so for a small Weber number. And lastly, the most simplistic type of coarse-grained model for the amplitude of the thin film is the Kuramoto-Zhibuszynski amplitude equation, which in addition to the previous assumptions is derived by assuming a small deviation amplitude compared to the mean height of the film. And here I want to point out these two equations, Navier-Stokes and the Kuramoto-Zhibuszynski, because in our machine learning models, we're going to use the Kuramoto-Zhibuszynski as a low fidelity model for which we can learn corrections to our data. Okay, so further to give you a general idea of the objective of the paper. So we perform simulations of this type of thin film flow. In our cases, we consider a vertical plane, and we saw Navier-Stokes, but we know that it is numerically expensive, but we collected this high fidelity data. Here in this illustrative picture, you can see that the velocity field is parabolic, and you can reproduce different wave patterns for different Reynolds numbers for this flow. To understand the dynamics of this type of flow, tracking the amplitude of the wave is sufficient instead of the full velocity field that you can compute solving for Navier-Stokes, and is more expensive. As a result, coarse-grained models for the amplitude. In our case, we're going to use the low fidelity model of the Kuramoto-Zhibuszynski amplitude equation. We use it to learn the dynamics of the amplitude as a model that supports the machine learning techniques. But again, this model is only valid under certain assumptions. And the data-driven workflow works such that we use the Navier-Stokes simulations from solving Navier-Stokes. And we learn data-driven models that can accurately describe the flow dynamics. And these models are models for the amplitude of the wave, one-dimensional models. And some of them are black box models that don't have any physical insight, and some of them have some physical insight from the Kuramoto-Zhibuszynski equation. And then we also derive models for computing the amplitude, the full field velocity, or the flow parameter, in this case, Reynolds numbers, from only partial measurements of the amplitude of the film. So this is the general objective of the paper. So first, how do we generate the high fidelity data? We have Navier-Stokes equations for this type of flow. They are two-dimensional, conservation of mass and momentum, and here are shown in non-dimensional form. We solve these equations, and we compute the corresponding velocity and pressure fields, and collected the Navier-Stokes data by solving them in COMSOL as a function of the Reynolds number in a range where the Kuramoto-Zhibuszynski is valid, and then when it starts to not be accurate. So beyond the limits of accuracy from which the KS was derived. The COMSOL solver uses a moving mesh with no slip condition at the interface and periodic boundary conditions at the lateral boundaries. And the kinematic boundary condition is such that the velocity of the interface that is normal to the boundary should be equal to the velocity of the fluid that is also not in that direction. And this ensures that there is no mass transfer through the interface. And a moving mesh is solved using the arbitrary and Lagrangian Eulerian description. So now to give you some perspective on the low fidelity model, the Kuramoto-Zhiwen equation can be derived from the previous equations that I showed you for Navier-Stokes, assuming a small wave number and a small Reynolds number. Here, the Kuramoto-Zhiwen equation is at the top of the slide. And so you can see that the variables, the time variable tau and the spatial variable c, they are different from the spatial and temporal variables previously shown in Navier-Stokes. And these are derived after, well, the equation is derived by eliminating higher order terms using asymptotic expansion. And there is, and these variables are derived by changing the coordinate frame and doing some additional changes. So yeah. And then through these derivations, you can obtain a relationship between the Reynolds number and the alpha parameter. Here, I'm showing the expressions for the correlations, either as a function of other dimensionless numbers or fluid properties. In addition, we validated that the derived relation between the Reynolds number and the alpha parameter is valid by comparing the critical Reynolds numbers of the KS and the critical Reynolds number of other reduced order model for the amplitude, in this case for the Benny equation. And what is the critical Reynolds number? It represents the transition from having a wave that has zero deviation from the amplitude, so it's a flat wave, and a wave that transitions with non-zero deviation from the average amplitude. And this corresponds to an alpha value of 4 and represents the first bifurcation point of the long-term dynamics of this type of flow. So how are the dynamics of the Kuramoto-Zhiwen equation? They are dependent on the alpha parameter. And we approximate the solution of the Kuramoto-Zhiwen as a Fourier series expansion in H terms. And in addition, this allows us to understand the dynamics of the KS, in addition to solving it. The long-term behavior of the trajectories has an attractor that is a stable fixed point for alpha equals 4, as you can see in the picture, where the blue represents the trajectories close to the initial time and the red represents the long-time trajectories. A phase plane of the transient corresponding to the second sine and cosine coefficients A2 and B2, here shown in the plot, shows that approaches a stable rotating wave for alpha equals 16. And a phase plane projection for also these coefficients for alpha equals 70.75 shows that the solution approaches a pulsing wave. And you can see this clearly from the reconstructed solution for alpha equals 17.75, where there are p over 2 translations in the spatial domain, and this corresponds to pulsing waves. So we can use so as I said, we approximated the solution of the KS by expanding in the first H Fourier modes, and we can an autoencoder and diffusion maps that I'll explain later about these techniques can be used to find the dimension of the true inertial manifold from those coefficients. And in this case, we found that the manifold is 3-dimensional and embedded in the H-dimensional space of those H Fourier modes. So the bifurcation diagram was computed, and the bifurcation diagram tells us information about the long-term solution. Here they represented as the L2 norm of the amplitude of the wave as a function of the bifurcation parameter, either the Reynolds number or the alpha parameter, because we know that they are related to each other. And here, this bifurcation diagram allows us to show the limits of validity of the KS compared to the Navier-Stokes norm of the amplitude as a function of the alpha Reynolds-Lang parameter. And of course, in order to get this plot for comparing both solutions, we had to rescale them to one of this of each scales. In this case, to the Kuramoto-Zhibuszynski scale of reference. And we can see from this bifurcation diagram that both solutions predict similar results for a Reynolds number between 1 and about 3.5. And this is because in this range, the Kuramoto-Zhibuszynski is a steady-state solution in a comoving frame with a speed -3, whereas the Navier-Stokes solution is a traveling wave with constant shape and speed 3 in an Eulerian frame. But then past that point, past the second bifurcation point here at around 3.5, the speed of the wave increases and the KS is also traveling. And the KS solution starts to gradually deviate from the Navier-Stokes solution. And as I showed previously, at about alpha equals 17, the solution of the KS is a pulsing wave. So we start to have more complicated dynamics and for the KS and the solutions of both diverge. So so we want to, now that I've shown you about the dynamics of the KS and how we obtain the high fidelity data, the first objective of the paper is to be able to learn PDEs from high fidelity data, PDEs for the amplitude of the wave. The general approach to identify PDEs from data, this is a local approach, consists of measure fine scale data. Here in this illustrative general example view, which is the measure parameter and can be of any dimension, is computed in a spatial and temporal grid from which we can estimate the temporal and spatial derivatives locally. And we can also have a parameter P that is part of the function that we are learning as part of the input. And we want to learn the function f that computes the time derivative as a function of spatial derivatives, in this case using a neural network. And we will show how we can use automatic differentiation with numerical methods to approximate the PD function f with a neural network. So more specifically, like it was done in a previous paper in the group, a neural network that is recurrent in time, whose structure is based on a standard numerical method. Here we use prescribed finite differences in space for the input. And this is computed as pointwise evaluations instead of computing the spatial derivatives of different orders. And these are then fed in the input in the trainable portion of the network to compute the pointwise time derivatives. And we can apply this method to across the entire spatial domain. So you can see this as applied to the entire set of ODEs. Essentially, we are solving a PDE by evaluating the ODEs of the discretization. We could template this network in a Ron-Yakuta integrator, and the integrated solution results here in the paper in a qualitatively accurate attractor. So we are applying in our paper a similar principle, but using different ideas for machine learning. So the machine learning strategy here to learn the PDE for the one-dimensional PDE for the amplitude of the wave is that of the form of time derivative of the amplitude equals a function of spatial derivatives up to 4th order in this case, because we know the form of the KS, which is up to 4th order spatial derivatives, and of also the amplitude and a bifurcation parameter P. In this case, a bifurcation parameter that we consider because we are using data scale in Navier-Stokes scale is going to be the Reynolds number. We could also solve this in the KS reference frame. So the first strategy is a black box model where we learn the full right-hand side of the PDE. And then 2 other approaches will have some physical insight into our learning process. So In the gray box model, we learn a correction of the KS amplitude beyond Reynolds number where it is valid, as I showed previously in the bifurcation diagram. And a functional closure models where we learn the full right-hand side as function of observables of the KS equation. And finally, with the learned data-driven PD, we could integrate to reproduce the amplitude or extrapolate to different initial conditions. Or we could even perform bifurcation analysis because we consider the bifurcation parameter as part of the inputs to the learned model. So firstly, the black box approach approximates the time derivative function by a fully connected neural network. The inputs of the neural network are the amplitudes and the spatial derivatives of the amplitude as well as the Reynolds number, and this corresponds to discrete points from Navier-Stokes simulations. In every of the cases that I'll show regarding how we train these networks, we use the same network architecture implemented in TensorFlow, and we use 2 hidden layers with 20 neurons each, tan each activation function, mean square error loss function, and an Adam optimizer. So the machine learning part is very simple. And the learned PD was integrated using Ronjakuta. And here are the results from our model. So here are the attractors from integrating the learned PD and compared to the ground truth and Navier-Stokes high fidelity data for some values of the Reynolds number. And we can see that the match is actually very good. And for comparison purposes, the KS results are also shown, which are appropriately rescaled in order to compare them with the Navier-Stokes results. And we can see that in this case, the attractors are qualitatively accurate, but not quantitatively accurate, especially at about the second bifurcation point that happens at about the Reynolds number of 3.5.
So Cristina, sorry to interrupt. Yeah, I have a question. Could you go back to the previous slide?
Yeah.
So the results. Yeah. Here. So, what is the training range for Reynolds number when you train your neural networks?
Yeah, the training range I show here. It's actually we are going a bit beyond the second bifurcation point. Is this range that I'm showing here, more or less. So that we can now, as I show in the second approach, we can learn corrections to the KS because here the solutions don't match. So
yeah. So I'm wondering. So is it? I think the last figure you show in the results slide, we see some errors. So is that because of the out of distribution or because the training is not really accurate?
So the errors that you see, so there are no errors really. I mean, very small actually between the ground truth Navier-Stokes simulation data and the learned black box solution. The error that you see is from mostly is from when comparing with the KS solution, because the KS was derived from Navier-Stokes equation under restrictions of a small Reynolds number. So if the solution for when you increase the Reynolds number is going to, the attractor is not going to be accurate, right? So,
yeah. So here the error, but this is a relatively high Reynolds number.
Yeah.
So you said that the training range for Reynolds number, the maximum is around 5. So is it because of that? So it's a little bit out of distribution. So that's why there's some errors. So for the other 5 figures, I think the errors between the black box one and the ground truth is we cannot see it from naked eyes.
Yeah, I think you're right. And with more training, essentially you will get better. But yeah.
Yeah, thank you.
Yeah. And please feel free to interrupt me as I go again if there's something that is not clear. So as I was saying, for the gray box approach, now we want to include some physical intuition about the function. So the KS the Gromov-Szyuszynski equation is used here as an additive term to learn a data-driven model that corrects the KS solution for Reynolds numbers where the KS was not derived to be accurate. So remember, beyond the second bifurcation point. So in this case, the inputs are the same, but the output of the neural network is the difference between the Navier-Stokes time derivative and the KS time derivative. In this case, this approach can be thought of then as a residual neural network. Again, we have good predictions.
Excuse me, quick question. So this is Panos from Pacific Northwest National Lab. Can you go to the previous slide?
Yeah.
So we know that the KS equation has terms up to the fourth order, right?
Yeah.
So if you want your correction, why do you keep it only up to fourth order? Wouldn't you expect the correction to have higher order terms than fourth order?
I mean, yeah. So, yeah, for a I guess for a larger enough for this small range of Reynolds numbers, I mean, maybe if you include the higher Reynolds numbers, then yes. But so here the assumption that we are making is that for this simple flow, for this relatively small values of Reynolds number, the dynamics are very simplistic. We don't have transition to turbulence or anything like that, and just and the amplitude of the wave is a function of the velocity field, and so yeah, this is how the KS model actually is derived, by having the conservation of mass and momentum included in the kinematic boundary condition of the moving index.
Yeah, and another way to think about it, if you want to keep only up to fourth order, is that somehow you keep the functional form which is close to KS, but you compute new coefficients. It's like renormalizing a Kuramoto-Sivasinski equation. So, okay. So I think that this, like you said, this would work if you stay at Reynolds numbers which are close to the validity of KS.
Mm-hmm.
Okay, all right, thank you.
Yeah, but that's something worth checking. And yeah, thank you for the question.
Yep.
Yeah. Yeah, so so we have good predictions in the gray box for different Reynolds numbers as before, and with the advantage as compared to a black box that here we have some physical insight and is also very, very accurate. And now the last approach that we use here for learning our 1D PD for the amplitude. So here we also have the physical insight of the Kuramoto-Sivasinski equation, again implemented for the full range of Reynolds numbers that we have been considering. And here a neural network predicts the time derivative of the amplitude also, but for given inputs of discrete local values of the KS evaluated in time or space. Spatial or temporal derivatives of the KS as pointwise evaluations. And different approaches, different flavors are implemented here, and they are inspired by the Takem's embedding theorem, which states that we can recover missing variables and reconstruct the dynamics by giving a short time history of the variables that we can measure. But the different flavors here are that, for example, in model 1 and 2, what we do is that we have as inputs the KS different evaluations of the spatial derivatives of the Kuramoto-Sivasinski solution. In model 3, what we do is that we have a spatial delays. So different points in a space are considered as inputs for the same point in time. And the fourth model is like the traditional Takem's embedding theorem model, in which we have time delays for the same point in a space as inputs. And here are the results of the performance for the 4 cases, which are good in all cases, comparing the attractors as well as the amplitude at the last integrated time step. And now I'm going to move on to the last objective of the paper, which was so if we have missing in fluid mechanics, missing data is an important problem in applications where you want to make measurements of the flow and also for monitoring purposes. So for example, in thin film flow applications, which is the case presented here, it is easy to experimentally measure the height of the film, right? Whereas if you want the detailed underlying flow field, so for example, the velocity field, that is more difficult to measure. And traditionally, I mean, there are techniques out there to actually measure the velocity field of different types of flow. So for example, one of them is particle image velocimetry, where particles in the flow are tracked with a video or photos, and from there you can infer the velocity field. But this technique is non-trivial, it's expensive. It is not as easy as to just measure the surface, right? To measure the height from the surface. So instead, the proposed approach is that we can measure amplitude, the amplitude of this thin film at selected locations. For example, here shown in the blue dots along the interface. And from there, you can infer the velocity field under the surface of the wave. And this tool that I'm going to describe is an accurate predictive tool, and regardless of where you have the sensor location, as long as you have enough measurements. So how does it work? So we use Navier-Stokes high fidelity data previously computed. And the known computed values, which are the height of the film at some locations, are used to predict the height of the film, the velocity field, and the Reynolds number at all the points in space, and for different time steps. And GAPI POD is a technique that is available out there in different papers and has been shown for this objective. And GAPI POD, what it does is that it recovers missing information from a vector that belongs to a subspace that is spanned by a few POD modes. And the missing data is obtained by performing interpolation in this reduced space. In the new method that we propose in the paper, we are using diffusion maps instead of proper orthogonal decomposition to parameterize a reduced space. And because this is a nonlinear reduction technique, it is using less modes than POD. And in addition, in GAPI POD, the accuracy of the methodology is affected by the location of the known elements of the vector. And I'll show that this doesn't happen with diffusion maps. So first, I'll describe for illustrative purposes the GAPI POD method. So firstly, proper orthogonal decomposition is implemented. The full data set, which as I mentioned, corresponds to amplitude, velocity, and Reynolds number, is split into train and test set. And we perform POD on the training set to obtain the POD basis functions. In POD, we keep as many modes as up to an acceptable reconstruction error of the original data. Then for GAPI POD, for GAPI proper orthogonal decomposition, we assume that the test set is spanned by the same POD basis functions as the training set. And the objective in this case is to find the coefficients C partial here that reconstruct the full solution of the test set from only partial measurements. In this case, from if we only know the amplitude out of the full test set. A measurement matrix M here determines the location of the missing data in the test set as zeros, and the locations where the data is known as ones. The coefficients C partial that allows us to reconstruct the full test data are obtained by solving an optimization problem. Note that these coefficients C partial depend on the gapping matrix M here, this M, which is influenced by the location of the known elements of the vector through this through the measurement matrix small m here, and the phi here, sorry, are the POD bases. So now I'm going to describe the GAPI-D maps methodology. So for GAPI-D maps, first we need to derive the low-dimensional embedding of our data. Now instead of with POD, with diffusion maps. And as an example of what diffusion maps does, let's consider this illustrative example of a 3D data set corresponding to the Swiss roll. And with diffusion maps, we find a map from the ambient space, from the 3D data set, to the corresponding reduced space, which here is two-dimensional. It can be spanned by phi1 and phi2. So how do we obtain this phi1 and phi2 using diffusion maps? We first start with an ensemble of vectors and compute a pairwise affinity function. And after normalization of this pairwise affinity function, we can get a Markov matrix. The components of a few eigenmodes from this Markov matrix, the ones that are non-harmonic, gives the coordinates in the reduced space. So here phi1 and phi2 are non-harmonics. The diffusion maps is the nonlinear counterpart of POD. And so first I show you that with POD, what we do is that we retain the first dominance modes. Here, when they are not necessarily the dominant ones, but the non-harmonic. But what is this term of being non-harmonic? As I said, not all the eigenvectors parameterize independent directions. Most span the same direction, but with different frequencies. The eigenvectors that parameterize the same directions are the ones that are considered harmonics, and the ones that parameterize independent ones are the non-harmonics. So how do we determine these non-harmonics independent directions for diffusion maps? Here again, in this example of the 3D Swiss roll data set, visually, we can easily identify the non-harmonic eigenvectors. So if we make a plot where the x-axis is the variation in the color of the Swiss roll, which is happening along the arc length, and the y-axis we plot the y-coordinate, which is the width of the Swiss roll in the 3D plot. We can see that there is a 2D variation of the arc length and the width of the roll. Hence, these are non-harmonic directions. They span different directions because there is a two-dimensional variation in these two coordinates. On the contrary, on the other plot, what I'm trying to show you is that any other combination of directions are harmonic because you can represent one as a function of the other. But this is a visual representation. In some cases, it's going to be more difficult to identify which are the non-harmonic variables. So a more quantitative approach will be using an algorithm that was developed in the group and identify these non-harmonic eigenvectors. What it does essentially is a local linear function is used to fit its diffusion map coordinate as a function of previous coordinates. And if this diffusion map coordinate can be accurately expressed as a function of the previous diffusion map coordinates, then that means that it's not a new direction on the data set if you can find that function relation. If this eigendirection is not a function of the previous eigenvectors, then obviously it's an independent eigendirection. And how can we then quantify the fit of this linear function relation? By computing this matrix Rk here. So essentially, if you have a small value of Rk, then that means that the eigendirection is an harmonic function of the previous eigenmodes because the fit was good, the linear fit was good. And now Nystrom extension, what it does is that if we have a new point in the ambient space, we can find the coordinates we can find the corresponding coordinates in the reduced space, in the diffusion map space. And this allows us to avoid recomputing diffusion maps to include this new point. And what it does is that it finds the distances between the new point and the points in the original data set, and then use this kernel to extend the functions in diffusion map space that were previously computed. In a similar idea, using a similar idea as Nystrom, if we want to find the inverse mapping, so F inverse here in the picture, from the reduced diffusion map space back to the ambient space, there's a technique called geometric harmonics, which can be thought of as a type of an interpolation method, like a neural network. And so what it does is that we define a kernel on the reduced space, find the eigenmodes, and geometric harmonics is the extension of these eigenmodes by using the Nystrom extension to include the new point. These interpolation functions are used to find the coordinates of the new point in the ambient space. And so in more detail, exactly what it's doing is that geometric harmonics compute the eigenfunctions of a positive semi-definite matrix K. For the mapping F from the ambient to the reduced space for the new point X new, geometric harmonics is extended by computing the step 2 here, shown here, which is like Nystrom extension, but for functions instead of for the points in the ambient space. And then the inverse mapping F is obtained in step 3 at the new point, where the new point is computed as a linear combination of the extended geometric harmonics functions. And double diffusion maps is also implemented because from the ambient space of the Swiss roll, which was n-dimensional to go to the 2 coordinates in the reduced space, to do this, eigenmodes were omitted, the ones that are harmonic, but because they are redundant for the restriction step. However, if you want to go back to a lifting space, then the redundant eigenmodes are important in order to make accurate interpolation. And we find a way to recover the omitted eigenmodes by taking the eigenmodes that we identified during the restriction step and compute diffusion maps in these two coordinates. Now retain a number of such eigenvectors and use them for interpolation, and this way we can recover the information that was lost during the restriction step. So how do we implement all these techniques? So the first step is to define functions on the available data by first computing the eigenvectors as a finite representation of eigenfunctions and use them as a new parametrization. In this case, when we do diffusion maps on the available data, 3 diffusion maps are retained for the reduction or restriction step. Then we randomly split the data and target values, so the fits that we obtain using diffusion maps in the previous step, into a training and test set, both of them. And we compute the diffusion maps coordinates which are required now for interpolation on the training data. These coordinates are used as functional bases, which means that we take the eigenvectors ordered by corresponding eigenvalue, and we don't need to select the coordinates as for the dimensional reduction. The goal here is to compute the target values, the phis, that correspond to the test data. So we want to find the mapping from the test data to the reduced coordinates, and we use geometric harmonics for the interpolation between the training data and the coordinates, the phi coordinates for the training data from the last computed diffusion maps coordinates. Then secondly, we use geometric harmonics for interpolation to find the inverse of the dimensional reduction transformation. Same as before, but now we want to interpolate the excess, so the training data defined on the diffusion maps coordinates for the inverse mapping. And in this case, we compute another round of diffusion maps. This is the double diffusion maps methodology that I showed before, to go back to the ambient space. But this time, the diffusion maps is implemented on the diffusion maps coordinates instead of on the training data. And then we interpolate the data as function values on the newly computed diffusion map coordinates. So since we have computed the latent variables and the diffusion map and the maps to and from the latent space, now we use all these tools to recover the full velocity and Reynolds number space from partial measurements of the amplitude. Firstly, by finding a map to interpolate from only amplitude measurements of the training set to the latent variables of the training set computed in the previous slide. And secondly, map the newly interpolated functions in the latent space back to the ambient space using the inverse mapping computed in the previous slide to recover the full data set. So here's a schematic representation of the GAPI diffusion maps workflow. The diffusion map coordinates of the full data set are firstly discovered, and then for partial data, in this case for only knowing the amplitude at some points, the latent space variables are computed using diffusion maps. And then geometric harmonics interpolation is used to recover the full data set. So going from the ambient to the reduced space with diffusion maps, and from the reduced space back to the ambient space with geometric harmonics is a structure similar to what happens in an autoencoder. But in this case, instead of having geometric harmonics and diffusion maps, we have neural networks where the inputs are equal to the outputs. The encoder step of the autoencoder is equivalent to using diffusion maps, and the decoder step is similar to using geometric harmonics. And a similar idea was implemented in another paper. So in that case, we had a multi-phase bubbly flow, and we use a global approach to reduce the dimension of the system that includes using proportional decomposition and autoencoders. In this system, the important variables are the average vertical velocity of the liquid and the average wave fraction, which are two-dimensional arrays in one space and time variables. The data after scaling and concatenation, we do POD on the fluctuation with respect to the mean for this data set. And we selected 10 principal components and further reduced the dimension of the 10 largest principal components using autoencoder, where the determinant Jacobian of the first part of the encoder is non-zero. Hence, we could define a mapping from the two neurons to the dominant PODs because it is invertible, and show that we can train a multilayer perceptron from the first two outputs of the autoencoder and back to the two neurons in the encoding layer of the autoencoder, proving that there is a bijection or a one-to-one mapping here. So this shows that the POD modes, because the POD modes are not necessarily nonlinear independent, that's why we can further reduce the dimension of these POD modes. So 10 are linearly independent, but 2 are nonlinearly independent. And the decoding layer is a function of the encoding layer of the autoencoder. But since the two dominant POD modes are in the decoding layer have the same information as the encoding layer, we can find a map from the two neurons to the top modes and then learn a multilayer perceptron for the remaining 8 POD modes. So similar, I'm illustrating this as a similar idea to the previous idea of GAPI diffusion maps to recover missing information, that is where you can learn a function from some of the data to the missing data. So, but continuing with this approach, we learn the dynamics of the leading POD modes, and then we reconstructed the remaining 8 POD modes using the learned multilayer perceptron. And we were successful at using this method to reconstruct the the variables that were of importance here, which were the vertical velocity of the liquid and the average wave fraction. So going back after this illustration of a similar idea and going back to the results of using Guppy POD and Guppy diffusion maps for thin film flow. So here the results from using Guppy POD shows that here in the first row, I'm showing where we can measure the data, where we have the proofs where we measure the amplitude of the wave along the interface. For the first case, we have 80 points that are equidistant along the interface. For the second column, we have 8 points that are also equidistant. And for the last example, we have the 40 points that are only known in half the spatial domain. And at those locations, we are measuring the amplitude of the wave, and we are using Guppy POD and Guppy diffusion maps. But here the results are for Guppy POD to reconstruct from those measurements the full velocity contours. So the POD, as I mentioned, the POD bases were determined based on the reconstruction error from the true Navier-Stokes data, and that led to 6 POD modes that were needed here for accurate reconstruction. And we can see that from these results of using Guppy POD in this case, there is for the cases where the measurements are equidistant, the error is similar, about 8. But for the case where we only have data known in half the spatial domain, the error was too large to use this technique for accurate reconstruction. For diffusion maps, however, what we had is that firstly, we have a more sparse representation of the data set because only 3 diffusion map coordinates describe our data. And second, it is also more accurate because, as you can see in the results of the reconstruction error, the error is about 4.5%, the maximum for all cases, and showing that, in addition, this technique is not influenced by the location of the missing data. So the first advantage of more clearly illustrating the advantage of diffusion maps, this figure taken from a paper by Koronaki et al. In 2023. The first advantage is that, as shown for this dynamical system here, is that in the first figure, the direction of the first POD basis vector, U1, that parameterizes the data, does not fully expand the nonlinearity. And so to accurately describe a point of this dynamical system, you will also need the coordinate U2 for the POD parameterization. But the second figure here, B, shows that actually U2 is a function of U1, and because there is this nonlinear dependence, you can learn that nonlinear dependence using diffusion maps, and it will give you that just one parameter is needed to fully describe the data. So yeah, so the parameterization of diffusion maps is more sparse than with POD. So that's the first advantage. The second advantage is that as I illustrated, in Guppy POD, the accuracy of the method is influenced by the location of the known elements of the vector. And the reason is numerical. It comes from the condition number of the Guppy matrix here, M, where the phi's are the selected POD bases, and the small m here is the mask matrix that defines which elements of the vector are known. So it depends on the mask matrix, where you have information about where the data is missing. So and also mention that for Guppy diffusion maps, the number of partial observations required to define the interpolated function is dictated by the witness embedding theorem, where 2n+1 independent observations are sufficient to create an embedding for an n-dimensional manifold here. since the reduced manifold is three-dimensional, we needed at least 7 partial observations of the amplitude of the wave along the interface in order to get accurate predictions for Guppy diffusion maps. And so now the conclusions of the paper to finalize. We use high fidelity Navier-Stokes simulations for 2 purposes. Firstly, we learn data-driven PDEs to predict the amplitude of the wave from observed Navier-Stokes data over a range of Reynolds number using 3 different methods. A black box method that was purely data-driven and physics agnostic, and then 2 other methods that had some physics in it. The gray box is a calibration where we learn the additive correction of the coarse-grained low-fidelity Kuramoto-Zhibosinski equation model. And the functional closure model, which inspired by Atkinson-Bain theorem, we use some observations of this coarse-scale inaccurate Kuramoto-Zhibosinski model. And the second objective of the paper was that, okay, so if we are able to learn the dynamics of the amplitude, but if we want to be able to make to determine the full velocity field, like you will get if you were able to solve the full Navier-Stokes, this is another interesting question. You can use Guppy diffusion maps or Guppy POD. For Guppy POD, Guppy POD is based on principal components, a linear method. This requires, if the data is highly nonlinear, it requires more bases to expand the data set. And it's also dependent on where the data is missing, so it's also less accurate. For diffusion maps, it's a nonlinear manifold method, and we have shown some of the advantages of using this. And if so, the results of that I'm presenting today are published in arXiv, and I want to acknowledge the co-authors of the paper. Firstly, my thesis advisor, Professor Yanis Kevrikidis. Secondly, Eleni Koronaki, who is a postdoc in Luxembourg, and Professor Karapetsas, who is a professor in Greece, and Yorgos Sarelis, that is doing his postdoc in MIT. And with that, thank you very much for your time, and I'll take any questions. Thank you.
Thank you, Cristina, for your wonderful talk. I actually have a question. Could you go back to the slides where you show the comparison between your method and the autoencoder?
Yeah.
Yeah, here. So, right, so here. So for this method, you use partial data to reconstruct the whole high-dimensional vector, right?
So first, the diffusion maps is learned from including some of the velocity data.
Right. So my question, could you go to the next slide?
Yeah.
So here in autoencoder, we're pretty familiar with autoencoders. So I'm wondering, how do you achieve this recovering missing data using autoencoder? Like, say, for instance, you have the data here, and those data are missing, and then how do we use autoencoder to recover it?
So I think that for autoencoders, you will not be able to do this interpolation.
Right. No, we can't do that.
No. Yeah, but I show some similar idea in terms of this, if you have that, if you know that the input and outputs are nonlinear dependent, then you can learn mappings of some part of the outputs and reconstruct the remaining information using some function like a neural network or a geometric harmonics. And yeah, but I believe you will not be able to do the same as what I have illustrated with Guppy diffusion maps in an autoencoder.
Right. Okay. Thank you. Do we have any more questions from the audience? Any comments? All right. Okay. So then, if there's no question, let's end this this week's seminar. So everyone have a good weekend, and see you next week. Thank you, Cristina, for your talk.
Thank you so much.
Bye.
Thank you.